Good morning, everybody. It's my pleasure to welcome Ted Adelson this morning. You might, if you haven't met Ted yet, it's perhaps because he's a member of Brain and Cognitive Sciences and Computer Science and AI Lab, but he's become a roboticist recently, despite a background in visual perception. And I found in talking to him about manipulation, not only does he have this fantastic technology and GelSight that he's going to tell you about today, he's got this really very, very interesting background that makes him look at the problems that we're looking at too, but in a very, very different way. And I found it extremely interesting talking to him about it, and I think you're in for a treat today. So, Ted, thanks for presenting.
Thank you. Okay, so let me, I think I'm not a roboticist, not nearly, and the most interesting thoughts I had were inspired by having children. I'm a vision guy, so I thought when I had kids that I would be fascinated by their visual system and see how that developed. But babies really don't have very good visual systems, in spite of what you might hear. And they are very tactily oriented. I became fascinated by the way they use touch and how important it is. And here's an example. This is my daughter Robin. She's a few months old. She can't even sit up by herself, so she has to be in that funny chair. But what does she do? She just feels everything all the time, and very skillfully. She's feeling all the textures, and when she gets bored with that toy, she starts feeling the textures of everything else around her, that smooth stuff, moving her fingers around. And not only that, from very early on, she's very skilled at manipulation. This is actually on her 1-year birthday. We were in Italy, and she was confronted with a new kind of pasta she'd never seen before. I don't even know what you call it. It's certainly a kind of round thing. But she quickly figured out how to manipulate it, which is, it's just the right size to stick her finger into it. And obviously, I never taught her to do that. No one taught her to do that. She just, because she's always trying everything and feeling it, she's always figuring out how to do things. So that's very impressive. I was just bowled over by all this and really wondered what in the world is going on in her brain to allow her to do all this. And so I asked my robotics friends, I said, well, what do you guys know about the sort of the way touch is used to support that sort of exploration manipulation? They said, well, for that sort of thing, really nobody knows much of anything, because first of all, nobody can even tell you what the physical signal is that the finger is getting, because you need something that's soft like a finger and something that has very high sensitivity, and there just aren't any sensors like that. So that's in 2006 when I started getting interested in this. But since I'm a vision guy, my thought was, well, is there some way we can take this mechanical signal at the fingertip and turn it into a visual signal? Because then I'm comfortable, I have some idea about what to do with that. And I should say, this is, I'll be telling you about this GelSight fingertip. It's certainly not the only soft, sensitive fingertip. There's some, here's some examples of other ones. Ferrier and Brockett at Harvard built something that's in some ways very similar to what we're doing. There's a finger made of rubber with a camera inside looking out and looking at the distortion, but sort of overall geometrical distortions of the fingertip. There's a Japanese group who built something called GelForce, which is specifically designed to measure shear. They have a bunch of markers sort of floating within this gel volume, and they measure the distortions. And then there's this very important soft sensor, which is very much like a human finger. It's not an optical sensor. It uses fluid pressure to get roughly a 5 by 5 array of touch sensors. It also has thermal sensing, and that's a really great sensor, and it's actually commercially available. But I will tell you about the things we can do with this alternate technology, GelSight. And as I said, the idea is we're going to convert these mechanical patterns, pressure, distortion, etc., into images. And we start with the slab of clear elastomer. That can be any old elastomer you want. Cover it with basically paint it with an elastomeric paint. In this case, it's got some slightly shiny pigment in it. And when you press this Oreo cookie against it and you look from underneath, you can see the shape. Why can you see the shape? Well, it's just in some random illumination, but whatever the direction of the illumination is, it casts some shadows and shading. Your eye is accustomed to interpreting that as the 3D surface, and with machine vision we can turn it into an actual 3D estimate of 3D surface that's shown on the right. And the easy way to do that is to use this classic technique called photometric stereo. The hard way to do that is to use one view shape from shading, which is just very, very hard. But there's this technique in the textbooks you always read about called photometric stereo. It says if the light's coming on something and casting a shading pattern from this direction, it's ambiguous. You can't tell from looking at a pixel exactly what the surface normal is. But if you have this light and separately this light and separately this light, 3 or more lights, like for example red, green, and blue lights, then you can constrain every point and figure out the surface normal, no problem. And then you integrate the surface normals to retrieve the height map if that's what you're after. And it's really simple, and it's really powerful, and it's, as I say, it's in all the textbooks, and nobody uses it. And why is that? I think we're the only people who use this commercially, as far as I know. There are these assumptions. So you have to have certain optical properties to your surface. They have to be known. You have to know where your lights are, and you have to have at least 3 of them. And if you've got a robot moving around the world, you just don't have the luxury of having everything painted and knowing exactly where the lights are. But we do have that luxury here because we made this membrane so we can make the optics be whatever we want, and we can put the lights wherever we want. So we're in this luxurious position of being able to use this great technique. And we can make it run in real time, so you can see the rolling Oreo. That's a big chunk of this elastomeric material. On the left, there's a camera underneath and some lights. And if we go in the soft direction, you can see really soft stuff, like here's my tongue. That's giving you, your eyes, the visual information. That's not a 3D reconstruction, but it's the visualization, and it could be turned into 3D. And there's other fun things, like here's a finger with lotion under it. Put some lotion down and they rub his finger, and you can see the lotion slowly gets pushed away, and you finally see the fingertip. Here's, again, the lotion forms a cushion underneath it. As you keep on rubbing, the cushion goes away. You see the finger better and better. The friction gets higher and higher. So you can see what's going on at the surface. This is exfoliating cream for your face. It's got little scrubbing particles in it to help you get the skin off. And this is chunky peanut butter, in case you were interested in what chunky peanut butter looks like when you're rubbing it on your face. At any rate, so that's just a slab of this stuff, and it can extract all kinds of interesting information that would otherwise be very difficult to measure. Okay, so that's sort of how this got started, and there are these extra constraints. So I'm a vision guy, human vision and computer vision, so I don't know anything about anything that's in here. And there was no money, initially no money to even get started, so everything had to be done very cheap. Didn't have any equipment, and most important, no expertise, and therefore a strong need for collaborators. And I continue to have a strong need for collaborators. And the first important collaborator is Srinivasan, shown here. Some of you may know him. He's in mechanical engineering in RLE, and he's an expert on both human haptics and machine haptics. And so working with him and a MIT student, Javan and Gia, we asked whether we could measure whether we could find a hard lump, such as you might want to do when looking for lumps like tumors. And so on the left you see on the left is the pink stuff is a lump of flesh-like elastomer. It's got a hard ball embedded in it. We're going to come at it from above with our GelSight sensor, and as we press, it distorts. But where the hard lump is, it resists being distorted. So as we press over time, we can infer the hardness under those different places. And on the right are shown some of these distortion maps indicating hardness. And we did this with the GelSight sensor, and we had humans do it, and we found that the sensor was more sensitive than humans, modestly but convincingly more sensitive than humans. At least us. Don't want to make any claims about experts who do this for a living. And so this was encouraging in our first real piece of haptic work, but we have not pursued it, the lump detection, because there are lots of technologies that can do this sort of thing, that have this, that can measure it's a low resolution problem, because the lump is a low resolution thing. It's somewhat big, it's buried, so it's sort of fuzzy. So it's not really what we can do best. And what we're really good at is high resolution and shear. And let me tell you what happened next. I'm going to take you on a detour away from haptics, which is that we put together a YouTube video. We were very excited by the fact that we could really measure very high resolution, but we weren't sure what that was good for. It looked to us like it must be good for something. So we made this video, posted on YouTube. So there's Timo's finger on a piece of GelSight. It's just again, a chunk of this material. And as he presses on it, it deforms, and you can see the details of his fingerprint. And that's because we've got this we've got this gold flake paint. Here's a different kind of paint. This is especially good for high resolution of fingers. A soft gel here. High resolution of skin measurement. Soft gel again measuring. That's my foot, which really looks ugly. Here's a post-it note. Look from the back at high resolution. We can see the fibers. We can see little bits of glue. This is because the GelSight covers up those materials. They are naturally clear or translucent. GelSight makes them opaque. It basically acts as paint that takes something that's otherwise transparent or translucent and makes it look like it's covered with gray paint. So we can get very high resolution, and we can also build a device to do this quickly. This one does photometric stereo with with 6 different lights to get a more robust result. And here's what happens if we press that. Our high resolution version gets $20 bill. You can see the 3D topography. And then this is an example of a surface that's difficult for traditional optical 3D measurement techniques like laser scanning because it's metal, light reflects. It's just a big challenge to measure it. But with GelSight, it's very easy because GelSight doesn't care about the optical properties of the material. It just quickly covers it up with its own paint and then can give you back a 3D shape. All right, so we posted that on YouTube, and it sat there for a little while. Somebody somehow picked it up on a blog. It went out, and then lots of people started sending it around. So we got lots of interest from people saying all kinds of things that they wanted to do with it. And so we decided this sounds interesting. Let's do a startup. So this is my first startup, which is exciting for me. I'm learning an awful lot of all the ways a startup can fail, which is, I'll tell you, if you're doing a startup, that's what you have to worry about, not whether your startup will succeed. So all the ways it can fail, but so far we haven't failed. But anyway, we do not make robot fingers. We don't measure hardness or pressure. We don't measure shear or slip, things I'll talk about later. We just do this high-resolution surface metrology because that is what most of the people who contacted us were interested in doing. Because people have a real need for it right now. They measure surfaces by various means, most of which are unsatisfactory. Anyway, so the company will sell you a benchtop scanner. That's our first device on the left. Very much prototype. On the right is one with a built onto an XYZ positioner, so we can take multiple measurements and scan over an area. And what do people use it for? Well, they measure surface roughness. That's a classic important measurement in machining, manufacturing. They measure, and it's difficult to measure well. Somebody at Tufts has used it for measuring tooth dental surface topography with normal enamel on the left and demineralized enamel on the right. People use it to measure coins. Coins, again, an example of a shiny material, therefore very challenging to image with optical techniques because the light just bounces off and goes all over the place. And probably the biggest application is manufacturing, inspection and quality assurance. Here's an example of a really challenging object. This is the lens on a cell phone camera. And what's challenging about it, again, for an optical system is, there's this flat piece of glass, and it's got this shiny metal bezel around it, and then it's got this shiny plastic mound around it. And it's just very difficult, by any means, to measure all of those things at the same time. But GelSight can do that because it just smushes down, the surface just clings everywhere, and then we can just do our little photometric stereo trick. And one of our customers said, this is the holy grail of measurement. Oops. And as I mentioned, we can also build up larger areas by stitching. Here we've written GelSight on a piece of paper. That depresses the paper. Then if we push the GelSight against the paper, we can see the depressions. But it's too big for a single measurement, so we stitch it together. There are people who are interested in printing artificial surfaces like leather who need to measure actually very large areas at high resolution. And GelSight can offer them that, for example, to do this piece of leather shown here. Here at MIT, Wojciech Matusik in CSAIL has one of these scanners. He uses it to evaluate 3D printing that he's doing. Normally, what they would have to do is do 3D printing and then take it to the scanning electron micrograph, which is a expensive, tedious thing to do. But here he's got this little device in his lab that he can just stick down and check whether he's making the shapes he thinks. And this is roughly a quote from him. He says it's great, and he invites other folks at MIT to stop by and try it if they're interested. There's also a device in the opposite direction. This is sort of low resolution, big scanning. Somebody is making a foot scanner, which is actually deployed, not in the United States, but elsewhere right now. There's a big chunk of GelSight, and you put your foot on it, and it measures your foot in 3D. What's better about this than measuring your foot in 3D in the air? Well, you're measuring it under load, so you can see how it deforms under load, which is often what you need to know. Anyway, so that's the end of that detour. Now let's come back to robotic touch. And the most important thing we need to do to make that possible is to make a compact sensor. And so this is the device made by Ray Lee, who's here somewhere and is going to give us the demo. There's Ray. The sensor shown on the left, it's basically a cubicle-shaped thing. The lights, to save space, they're coming down the sides and then they bounce over to illuminate the gel. There's 3 different colors of lights. There's a little camera in there. The gel's on the bottom. And Ray, why don't you come give us a demo? Questions while Ray sets up? Yes?
So what was like the key breakthrough for you to create the GelSight? Was it the actual gel material that didn't exist before, or just the idea of lighting it to get the 3D scans?
Just the basic idea of taking a piece of gel, painting it with a reflective material, and illuminating it obliquely so that you can see the relief. That's the key insight, and it's very strange to think that nobody did that before. But it seems that no one did that before, or if they did, they didn't exploit it. Yes?
So how robust is this coating? So if you put it on a robot finger, I can imagine that.
Yes. So I can give you a couple of answers to that. So the softer it is, the more delicate it is. The devices that we're selling for surface metrology, the company is selling, they have a medium hard piece of gel. and we didn't know how long they would last. Now, those aren't being used in a real rough environment by out of control robots doing crazy things. But they last. The pad will last for thousands of impressions doing those measurements, and I think that this particular device Ray has here probably would not last too long on the robot because it's pretty soft. But if you make it harder, the harder you make it, the tougher it can be. So if you think about a skateboard wheel, there are skateboard wheels that are made of clear polyurethane, and they're pretty hard. So they're not going to have the same level of sensitivity, but they have enough. And of course, they're quite tough since you can skateboard on them. So there's going to be this trade-off. All right, so Ray, what have you got to show us here?
So this is basically a 3D image reconstructed from the GelSight images.
Do you want to hold up the little cube device? Or just hold it up so they can see it. Okay, so it won't be
Yeah.
about this big.
Yeah. So basically the
You're probably not on camera. Is he visible?
Who had the last one, but it was much bigger.
So basically, this is the. So this is the latest version of the fingertip GelSight sensor. Reduced to the size of a cube, about 25 millimeter on each side. So we basically reduce some of the resolution, but care more about the real timeness, and still it can measure resolution of tens of microns. As you can see from here, when I press on it with my finger, you can see the ridges on my fingerprint. And so on the top left corner is the image looking from the top, where brightness corresponds to the height. And by this, when I press harder, the image will actually become brighter. So while it measures the surface textures, it also measures the amount of pressure I put on the sensor, which is very critical in robotic tactile sensing. And so let me measure something else. So if you have a $20 bill in your pocket, you can take it out and see. Also try to feel it with your finger.
And you can pass those $20 bills up to the front when you're happy.
Yeah, I'll be happy to take it. So this is basically the letter 2.
It's printed in this weird embossed way.
Yeah, and 0. And you look on the left side, there's also those very small prints saying this node is legal tender, something like that.
Each of those letters is about 1 millimeter high.
What's the depth resolution?
Yeah. For this one, it's also like tens of microns.
The fancy high resolution device is sub-micron, a tenth of a micron or something like that. And I should say that the commercial device, and it's a couple of microns in X and Y. It's an optical device, so it's you're up against optical limits in X and Y, but you can see anything better.
And this is my hair basically. You can see one on top of each other.
Show your shirt.
This is basically the surface texture of my shirt, and you can use this to do, let's say, surface texture classification. Let's say when a robot touches something, and you can immediately tell what that material is. Let's say in the future we can ask the robot to bring a soft tower for you, something like that. Yeah.
What is the latency?
Sorry?
Latency sensor?
The latency. As you can see here, so currently, let's say the frame rate itself is around 10 frames per second, and the latency is also like on the. We didn't measure that accurately, but it should be on the order of tens of milliseconds.
Tens of milliseconds.
Tens of milliseconds.
It's basically what you need to do. First, you have to have your camera. This is a webcam, which is not very fast. But you have your camera, and then you've got to do this a lookup operation to get the surface normals, and then you've got to do this Poisson inversion, which involves an FFT. So it's however fast you can do those operations, which that depends on how much resources you're going to throw at it.
So compared to the previous version, previous GelSight devices, this one is more like, sacrifice some of the resolution, but has higher speed, also much less expensive. As Ted said, we mentioned that we used a webcam and some 3D printed materials, and also some plates, LEDs, spotting plates, LEDs, etc. So the whole thing can be very inexpensive.
What's the resolution and frame rate on that?
This one? The camera itself, the frame rate is 30 frames per second. When you do the processing, with normal and shear force, etc., is around 10 frames per second.
In resolution on that one?
The resolution itself?
In pixels?
In pixels? Pixels, this one can be up to 1280 by 960.
It's way more than we need. It's just a webcam that has that resolution.
Yeah, and the resolution I'm showing here is 320 by 240, in case you're curious.
Is there a trade-off between the sensor size and the resolution besides the camera resolution?
Sorry?
Is there a trade-off between the size of the sensor area versus the resolution?
So, in the sense that if you want a larger area, you might need to move the camera a little bit away from the sensor itself. In that sense, yes, it has to do with the resolution. But if we use some other tricks, like to either using a wide angle lens or using extra reflective path, that part might be compensated.
So it seems that the sensor is kind of a flat sensor.
Yeah.
Right?
Yeah.
So the two related questions that I have in terms of robotic applications are kind of what's the smallest possible package you could put it in, or are there any considerations for if you have this on something that, it makes a lot of sense when you're sensing something that's flat, or when you only want to look at part of something that is that you can sense like a tangent to it, or that can squish into the gel. But if you're trying to sense around a surface or something like that, you might think that either you need some type of sensor that can bend, or you need lots of little facets at like a small resolution so that they can bend or something like that. Have you guys thought about that at all? Or what kind of the smallest package it can be in such that you can make multifaceted surfaces?
So currently, if you want the 3D reconstruction, this is somewhat limited by the illumination system. That's why in the previous systems we use we put the illumination further away from the sensor, so as to simulate like more parallel lines. In this case, in this very compact version, we are also limited by that. That's why we try to simulate parallel path. But if you want to make it very compact, it's sort of becomes more and more difficult to simulate that. But we can definitely make it smaller, around twice the size of human fingers, or even smaller, if we sacrifice some let's say accuracy.
So why don't I continue? We can come back to questions. I'll just say, in terms of what's possible, lots of things are possible. We definitely can make a very small one. We can make ones with weird shapes. All of these, everything just requires some amount of thought and effort. And some things are easier and some things are harder. If you have a specific case, I can talk to you about it. I would say, this use of an optical system of this sort, it has some advantages. I mean, you've got one of the main advantages is people make really cheap cameras, and so you can buy this really cheap sensor that's giving you all these measurements all the time, and you've got this thing that's soft, and so it's deforming, but it's relaying all that information through light, which is easier than trying to relay that through wires that have to bend. So there's some fundamentally nice things about this approach, but it's also limited in that you have to figure out how to get your camera and your lights and everything arranged right. And there are ways that you could really squeeze things down, but it'll take some special purpose hardware. All right, so that's our demo. Okay, so now that we've got a device that is appropriate for the robot, what can we do? So this is our next important collaborator, Rob Platt, who's at Northeastern, and who's a robotic manipulation guy. And the task that he was excited about is one I didn't even realize was important. Let's say you grab a USB cable, you've gotten there visually, you grab it, you don't know exactly the orientation, the exact pose of your fingers, and you're going to try to insert it somewhere. But with the GelSight, as shown on the right, it can pick up your shape of some significant markers on this device. It can figure out what the pose is exactly, and then you can do your planning and figure out how to do the insertion. That's, without going into any details on that, that's proven to be very successful. And then another version of the GelSight sensor involves the use of markers so that we can measure shear, we can measure these tangential forces. So it's basically just the same sensor except with a bunch of dots on it. And the camera just watches the dots. And we can sort of get both kinds of information, the height map as usual on the left, and we can track these markers to see what the shear, the displacement is. Most touch sensors out there cannot do shear. They can just tell you about local force or pressure. But shear is very important. Basically everything having to do with frictional interactions is conveyed through shear, and in particular the detection of slip when you are picking something up or moving it is a tangential problem. So it's really nice to be able to not only measure shear, but measure a shear field so you can see how it varies across the surface. And I'm going to skip a demo of that, but just show you this. video that Wenjin made. Whoops. Skip by that. All right, so there's a jig there that's holding this little bottle of some fluid, and she's just wiggling it and watching what happens. Why am I not being able to do this? Oh, okay, here we go. So it's just fun to watch, basically. Inside you've got all this stuff going on. And as you move it, so you see the shears, you see the torques, and if you move it further, you'll start to see the slip. You'll start to see interesting patterns happen as it slips. They're indicative of slip. And that brings us to this very important problem with dealing with slip. If you, let's say you're just doing something, you're picking an object up, and you're grasping an object and then you're picking it up. So what do you have to do? You go like this, you stop when you feel that you've touched it, that you've got it between your fingers. Then when you lift it up, you don't know how heavy it is, but it starts to exert this tangential force on your fingertips, and you've got to adjust your grip to prevent it from slipping. You've got to make sure the normal force of your grip is sufficient to prevent this tangential slip. But of course you don't want to crush your object, so you don't want to squeeze any harder than necessary. So here's a bunch of videos. This is a can of Red Bull. So this is the issue here is this is a heavy object. This is a heavy object which you need to grasp with some firmness so it doesn't slip from your grip. And there we go. It figures out how to adjust. And then here's an egg. And I want to emphasize there's no change of parameters. These are all run with exactly the same program, with the same parameters. So it's figuring out everything by itself. There's an egg. Fortunately, it did not crush it. It's a raw egg, isn't it?
Yeah, it's a raw.
All right, here's something more delicate. Strawberry. So why don't you just touch it very gently and lift it. All right, that's good. All right, now the big challenge of potato chip. Sitting here in a little bit of hummus. All right. Yes, success. All right.
So it's
Now-
looking for shear as you lift it up and then.
Well, there's
if it
almost
doesn't-
no shear in this case. So right.
Basically, we are using a normal force and added the shear with some slip detection. If there's slip, we just hold it a little bit tighter so that we hold an object with a minimum amount of force, but at the same time, it's not slip.
You protect slip and then if it slips, you squeeze more.
Yeah,
that doesn't help the mass of the object. Right?
So it actually, in this program, we never let it get to the point of slip. We
You never
actually
get that far, but how would you know when to stop pushing?
well, we can see how strong the tangential forces are, so we can, and we know, and we make some guesses about the friction, coefficient of friction, so we can tell how much force we're going to have to use to counteract, to overcome the potential slip. We've also done other things where we actually measured the slip, the incipient slip, and then the slip. But in this case, it's actually just measuring the tangential force and preventing the slip. All right, and just to be truthful, we have to admit that some potato chips were harmed in doing this demo, but mostly it works. All right, so directions to go in the future. We'd like to look at alternate shapes, for example, a more finger-like shape, something that can be more compact. We can put the camera inside the finger, looking down at the fingertip, and have a curved fingertip that has some advantages. If you want something that's really flattened out, have the camera looking at it this way, and we can have a microprism array that will redirect the light down onto the surface. And in this case, we use a retroreflective membrane. I mean, it's just very shiny, basically. So it comes back, the light comes back in the same direction it came from. There's people doing 3D printed optics. There's some people at Disney up on the left. Actually, they built a touch interface. This doesn't involve any elastomer or anything. It's just there's a bunch of fibers that can see where your fingers are. The fibers go straight to a sensor. There's no lenses or anything. Wojciech Matusik was involved in this similar effort, in this case mostly for making displays, but it's the same thing backwards. So we can exploit this kind of 3D printed optics in order to give us more flexibility in terms of our designs. And we can also think of going beyond fingers to touch sensing in the world around you. So you can make your steering wheel out of GelSight material, have cameras inside. It can tell who you are, it IDs you based on your fingerprints. It can also tell you what you're doing, saying you're too tense, going down, you're going to crash. Or in you can imagine in a washing machine or something, you've got some GelSight sensors in there, warning you that there's Velcro and your sweater is going to get messed up. Basically, anytime anything touches anything in the world, there's an interesting opportunity for touch sensing if you can figure out a way to get a sensor in there. GelSight is one technology that offers a lot of flexibility, so it might allow you to do a lot of things. All right, to summarize then, it's a versatile technology. You can make these sensors be hard or soft, big or small, various shapes, and we can use it to measure various things: shape, texture, manifold, shear, slip, and things. As I've said, I'm a vision guy, so I don't know about robotics or mechanical engineering. I need collaborators. And thanks to these people at MIT, you've heard about most of these already. Alvin Ruff and Forrester Cole also helped with some of the demos at Northeastern. Rob Platt's lab and these folks, Andres Tomas and Tomas here, Benjamin, who helped with a bunch of this stuff. And the startup, some of the demos come from the startup. That's Kino, Dennis Rohai, and Bill Yost. And thanks to our funders. And thank you for coming. Yes.
Can you say a little bit about what the calibration process is like to get data? Is it something that you can use for GelSight or for using it
Okay, so if you're using photometric stereo, you need to measure surface normals. So we have a little calibration device, which is a bunch of spheres. You press the spheres against it, you know where they are, you know what the surface normals are. You go over it, you build a lookup table that tells you how to extract surface normals. It's depending on how much you care about accuracy and depending on how soft the sensor is, you may have to do it more or less frequently. For a lot of stuff, especially a lot of robotic stuff, you really don't need such high accuracy, and you'll be able to get away with maybe doing one calibration at the beginning and probably not calibrating for a long time.
It sounded like you're actually using like measured values for like 10 channel forces, assuming a couple of descriptions. So what's the calibration process like to?
Oh, okay. So for these demos that you saw where we're interested in that, we don't actually have measurements of the friction. We're just hoping for the best. basically, and so far the best. Hopefully the best has worked. Makes some reasonable assumptions, and since we don't know what these objects are, can't have very full, strawberry, we don't know what they are, so we don't really know what the frictional properties are, but we do a sort of a medium guess as to what they're going to be, and so far it's succeeded. Yeah.
What forces does it saturate at? With the gels that you've been using?
What forces does it saturate at?
Yeah.
Well, that depends on how soft it is and how thick it is. The device that Ray is showing you is going to saturate pretty soon. I mean, you can saturate it just by pushing it with your finger because it's thin and soft and it starts to bottom out. But again, if you have a thick thing, you can it'll take longer to saturate, or if you have a hard thing. So it's going to depend, and it'll depend on your design constraints. We haven't experimented much with hard, tough elastomers, but we definitely should, because to make it practical for a real robot, that's what we're going to have to do. Yes.
It seems like to solve the forces, or something, you need to like solve some PDE or inverse PDE problem. Is that just for get like higher resolution, or is that something that you find your way out?
Well, there's a classic technique or a set of techniques for doing what they call solving Poisson's equation, which is taking all these derivatives and integrating them into this shape. It does have this problem that you're missing the DC. And the low frequencies are not very well extracted. But in practice, it works quickly and well enough for all the things we've tried. For precision work, you probably want to augment the photometric stereo with another source of information like binocular stereo or structured light or something like that. So you can really nail down the low frequencies. But for most robotic applications, of course, I don't know. I'm not a roboticist. I might be wrong. It seems like you don't need to get everything right in order to make good use of the information.
So to what extent do you think your daughter, when she's playing with the tag on the teddy bear, is she reasoning about fine geometry or stress? I mean, it seems like things that she's getting out of that experience might not be at the super low level tactile, but the broader motion of this thing, when I push it, it moves and things like that. I mean, what role do you think the zoomed in high resolution information that she's got in her fingertips essentially is playing in her development there? Do you think it's?
So she's, at the beginning, really excited about this little tag on this plush animal. Now, and let's assume that she's not excited because she's not visually. I mean, it's not just the visual. Even without the visual, she'd be excited. You probably know since you're a father that people actually sell toys that consist entirely of tags because they've discovered that ladies love tags on clothing so much. So you just get something that's covered with all different kinds of tags. That information is it's a piece of fabric. It's not exerting very high forces, and it's exerting it very locally. And to tell the texture of the tag from the texture of the flesh around it really requires that you measure high resolution information with very low forces. So that's my belief anyway. I can imagine you might get away with something cruder, but I think that is an important part of what she's.
Do you think the super fine tactile information is being learned about sort of before, object permanence and things like this? I mean, it seems like at some point you're touching things to watch what moves and get a sense of objects.
Yes, I don't know how it fits in, and how what are they building up? What's the model of the world they're building up? That's a big question, which I'm not prepared to solve. but a fascinating one. I mean, clearly there's, I mean, they practice all the time, right? They're just constantly touching things, they're constantly moving things, seeing what they do. So they're constantly building up this experience, these expectations. But what's the representation and how does that look?
It's actually, thank you very much. So for anybody who's not been here before, we've got outside and sort of this is social robotics lunch.